In part 3A, we're going to take a look at the Candohm resistor. We're going to calculate the necessary wattages for the replacement resistors. Ouch! Going to do some checks on this Candohm resistor. There's 3 sections in here, and I've got them marked here. So that's R11, R12, R13. R11 should be 220 ohms, R12 should be 33, and that R13 should be 52 ohms. So let's check and see what that's reading. So that's from here to here. That's about 251, should be 220. What is that? 12% out? That sound right? Let me do the math real quick. 220 divided by 251, 87, 13%. We could probably live with that if we had to. Now remember, the next section should be 33. Yeah, it's right over here. And that's reading 43. 33 to 43, that is 76%. So that's out. That's 20, 25, 26%. Now the next section should be 52, which, let's go right there. And that's reading 62-ish or so. And that's a little bit out. Or is it? 52 to 62, let's see. Divided by 60, call it 63. And that's 82%. So that section's good. So there's probably only one that's bad. But here's something to beware. If you'll look, there's the Candohm we just checked. Now this last section that we're on is supposed to be 52. All right, we're getting 63. Okay, but look at the end of that. What does that end say? What does that end say? That end says ground. So that means if I pick this lead up, if I pick this red lead up right here and put it on ground, I should get the same thing. Correct? I don't. So let's look a little closer at it. Okay, if you see how this is made, these 2 terminals, let me move this right there. You see these 2 terminals here, it's kind of got like fish paper or some sort of insulator to keep it from there. There's a strip of resistive material, probably carbon, in there, and that's insulated with that fish paper, and that's what happens. These things break down and short out at a certain period of time, you know. So it's always good to go ahead, and a lot of people will just change these out automatically. I have found some of them good. So are they subject to go south on you any minute? Yes. Yes, they are. But look at the last one. You see how that's got the fish paper insulating this tab from this bracket. Now this is a heat sink. This is how they get by with a small. It's a heat sink against that. And you'll see the next one, it is also insulated. But look at the last one. It appears, and maybe I can get down in there a little better. That appears, and rightfully so, should be connected to that which goes to ground. Okay? Now what I'm going to do, we're going to run a little experiment. We'll get it to where you guys can see. Let me set it up. Okay, I've got this lead on that end, and then I've got this on that one, and it's still reading our 60 ohms. Should be 52, but it's 60. But it should be reading to ground. Okay, we don't get that. Don't get that. Now I'm going to take a simple little dental tool, and I'm going to reach right down in here and see if I can short that. I have shorted that end to that the way it's supposed to be. Well, let me get the other end. I made it happen. I can make it happen again. There you go. Just takes a little pressure. Now, if that Candohm was good and you wanted to keep it, you could just tie that end to ground. We're probably going to build a Candohm resistor, leave this one in place, and just move the stuff over. It's probably what we're going to end up doing. But I just wanted to show you how, even though the resistance looks good, it lost its ground there. We're going to replace this Candohm. There's only one section that's really kind of out, but I'm going to go ahead and just replace it all here. Probably put a terminal strip in there and put 3 different resistors. Now, this is what you run into, and we're going to calculate the wattage of these resistors. Now, there's a lot of folks will take and put their terminal strip, and then they'll just put 5 watts all the way across, 10 watts all the way across, whatever the biggest one is, they'll just go all the way across, and there's nothing wrong with that. There's 2 things: price, they're not cheap, and also the amount of space it takes. So I'm not saying that you should scrimp or save or whatever. You definitely want the resistors to carry the wattage and dissipate the heat. More surface area, the bigger the wattage, the more it'll dissipate. Don't mean it won't get hot, but we're going to look at these. I've written these in. This is 220 ohms, 33 ohms, and 52 ohms. I think we covered that when we did the initial. Now, hopefully we can see this. I wish I could see this. The center tap of the transformer comes out to the bottom of the C13, which is a 8 microfarad capacitor. Then it runs over, and then it goes up to this pin, which is right here. And then it goes over, and it'll go through the field coil, 2500 ohms, and then it comes back out this pin, and it comes down and goes to the end of that 220 ohm resistor. So we know, and then through that resistor chain it goes to ground, and it sets the bias, and we've got the voltages listed here: minus 13 at this point, minus 4 at this point, and minus 2.5 at this point. Well, this really doesn't go anywhere, but this one and this one, they go, and then they go and they set the bias, the cathode bias and the grid bias of the 75 tube. Okay, so we can figure the wattage of these resistors based upon the numbers that are given. Now, a lot of times these numbers are not given anywhere. You have to trace it out and go up and see, like to the plate voltage. Sometimes the voltage divider does the plate voltages, so you have to go up and look at the plate voltages and figure out what the voltage at that point is. We're fortunate because we have these voltages, and so if we look right here, that 52 ohm resistor goes to ground. Well, we saw it didn't, but it's supposed to. But the voltage drop across that is 2.5 volts. We can use Ohm's Law to calculate these wattages. Now, you look at this and say that's 4 volts. Okay. And then we look at 13 volts. So from 13 volts to 4 volts, that's what's the voltage drop? You know, that's not the voltage drop. 13 volts is not the voltage drop. So it's 13 minus 4. I'll get into this on the whiteboard, but if you're not familiar with Ohm's Law, afraid of Ohm's Law, afraid of math, whatever, I would suggest that you watch some videos on Ohm's Law. It's a fairly simple thing once you dig into it. I would print one of these out and hang it up somewhere and reference it. I reference it. And I would like to think I know a little bit about Ohm's Law. But we're going to figure power, and so we're going to use it in this chart, this pie chart. If you were looking for voltage, then these are the formulas you would use. If you're looking for resistance, these are the formulas. If you're looking for current, these are the formulas. If you're looking for wattage or power, those are. So we'll use this quadrant today. All right, we're going to go to the whiteboard and we're going to calculate the wattage of each one of these resistors. And then later we'll talk a little bit about what wattage we're actually going to use to make sure that we're covered due to temperatures and just as a safety factor. But I just wanted to let you know that this board is an official whiteboard and it's sanctioned by Sky Carl. Thanks, Sky Carl. All right, where do we begin? You can begin on either one of these. But let's go ahead and get the low-hanging fruit at this point in time. I was looking for my other marker. Okay. Now we already covered this with the schematic, and this is, we know that this controls or goes to the grid bias of the 75 tube. So the current is going to be fairly low. If we have high current through that tube, we're going to have in our grid and our cathode, then we're going to have more of a problem anyway. So anyway, to determine the voltage, I've lost my pie chart. Okay, to determine our wattage, we know the voltage drop and the resistance. So we're going to use this particular, the power in watts is equal to the voltage squared divided by the resistance. Okay, so let's take this first one. This is 52 ohms, and we know the voltage drop is 2.5 because the voltage reading at this point to ground is 2.5. So we know that this is 2.5 volts. Okay, so let me get my handy dandy calculator. So we've got to square 2.5 volts. And that's just basically multiplying it by itself. 2.5 times 2.5, and that's 6. Let's write the formula up here. P in watts is equal to E squared divided by the resistance. Okay? So our power, 2.5 times 2.5 is 6.25, and we'll divide that by 52 ohms. So let's divide that, and that is, in wattage, is 0.120 watts. So a 1/4 watt resistor could handle that, 0.25 watts. Typical carbon composition resistors, they'll go up to about 250 degrees Fahrenheit, and then once you hit that temperature, then they start derating, which means that the resistance changes, and eventually over time, and you'll notice in the older radios, a lot of your carbon resistors have doubled in value or gone up in value over time, and that's environmental, that's heat, there's several things, just age will do that also. So what you want to do is you want to make sure you've got enough wattage when you're picking out your resistor to cover this, and it depends upon whose advice you're going by. Most people go 2 to 3 times the rating, just as a safety factor. You will have some folks say clear up to 5. If you're if I now this is me personal, if we're running plate voltages with higher currents out of this, and we're running 2 and 3 watts or what have you, then I will go 3 to 4 to 5. And you can get a 25 watt resistor to do this. But in this case, a 1/2 watt resistor will be fine, because that's almost 5 times. It's 4 times for sure. So let's go to this resistor. Let me erase the board, come right back. Okay, now let's look at this one. You look and you say 4 volts, and so you're thinking, okay, that's 4 volts. No, it's not dropping 4 volts. It's dropping from 4 volts to 2.5 volts. If you put from here to ground, you're going to see 4 volts, but that's this one included. So if you put your voltmeter from here to here, you're going to read the voltage drop across this resistor. And that would be 4 volts minus 2.5 volts, which is 1.5 volt. So we square that. 1.5 volt times 1.5 volt is 2 1/4. 2.25. And we'll divide that by your resistance, E squared over R, and that's 33. So our wattage for that, 2.25, let me punch this in, and we'll divide that by 33, and that is 0.068 watts. All right. That's lower than the other one, right? So another 1/2 watt resistor would be fine with that. Covered, not a problem. Let's do the other one. Had to re-record this part. I found out I didn't have my mic clipped on and sounded like I was in a hole. So let's recap. We've already determined that a 1/2 watt resistor would work on that one and a 1/2 watt would work on that. Now you can use 1 watt, 2 watt, 10 watt, 25 watt, whatever you want to, as long as it's above those calculations with a safety factor. And it depends, like I say, who you talk to. Some people will go 3 to 5 times that rating, and that takes care of the ambient heat, the derating. It's one thing to have a resistor sitting out on a table and the heat's just radiating off of it, but you're going to be under a chassis. There's a lot of factors to involve there. Now the Candohm resistor, remember, it was heat sink. It was against the cabinet, so it was dissipating the heat through the cabinet. So the safety factor, there's nothing wrong with going more, but you got to look at your price, the mounting, the size, all those things. But as long as you're 3 to 4 times greater than what you've calculated, you're going to be fine. All right. And you're going to get several different answers. You talk to different people, they're going to tell you all different. We like to, as Americans, we like to be conservative, and more is better. Remember that. And there's nothing wrong with it, really not. So let's figure the voltage drop across this. At this point, we're seeing minus 13 volts, and I've used negative. I haven't used the negative term, but all these are negative voltages, but the numbers still work out, negative or positive. So you're still going to have a voltage drop of 9 volts here, minus 13 to minus 4. That's a voltage drop of 9 volts. So 9 volts we insert in this, and so we square it or multiply it by itself, and that's 81. And we divide that by the resistance, which is 220. So now I'm going to have to go back to my handy dandy calculator. Remember when we didn't have calculators, people? Now here's a true story. I took my advanced ham radio test in front of the FCC and used a slide rule. True story. It was in Atlanta, Georgia. And I passed it, by the way. So there we go. Anyway, so 81 divided by 220 is equal to 0.368 watts. Okay? So that's less than a half. A half wouldn't be double. 1 watt would almost be 3. So to really be conservative, if you didn't have a 1.5 watts, I'd go with a 2 watter. Now, if you had 2 500s that were a watt apiece, you could put them in parallel, more surface area, close to the resistance. You can do combinations like that. But I'm going to have to probably order this one. So you're probably saying, why don't you just put 2 waters all the way across there? And you could. You could. And be safe. Be really safe. But anything over 1/2 watt, I think you're wasting. Now, it's just me personally. Let's look at what we just went over. The 52 ohm resistor, the 33 ohm resistor, and the 220 ohm resistor, we calculated that the wattage for that voltage drop was 0.12 watts. we decided we'd use a half a watt, and so that's a factor of times 4. So that 0.5 is 4 times greater than the rating, what we calculated. With the 33, we calculated at 0.068. We decided we would use a 0.5 resistor, and that's a factor of times 7, over times 7. The 220 ohm, we calculated to be 1/3 of a watt or so. And so we decided we would use a 2 watt, and that's a factor of 5. So I feel comfortable that that's going to take care of the heat and the current through those resistors. And I didn't use a power resistor or a wire wound resistor or anything like that. We're just using resistors that may very well be in my box. I don't think I have a 2 watt resistor, 220. I'm pretty sure I've got something similar or close to those two. Okay, I've installed the Candohm resistor, made all the connections. Okay, on the Candohm, indicated voltages are measured to the chassis with 119 volt lines set, not tuned to a strong signal. So we turn that off the signal, and so I've got the, if you'll remember the Candohm, the first one is supposed to be -13, the next junction is -4, and the next one is -2.5. So let's run in here and do a quick check. There is a -13.3. The next one is a -3.5, which that's fairly close. And then the next one is a -2.2. So that 2.2, that normally should be -2.5, and this one should be a -4, and it's a -3.5, but the other one is -13, which is on the money. So the Candohm seems to be working. The temperatures on these resistors are running cool. They're not hot at all. Well, these two, like I said earlier, I ended up putting 2 watts in there, even though I was going to put a half watt. Well, when I got to one of them, I didn't even have a half watt. I think it was the number, the 33 ohm, but or the 30 ohm. So I just, what I had in my box was 2 watts, so I put them all the way across there. So that's how that worked out. But I really think the half watt would have been fine. Okay, I hope that made sense, and hope you were able to use some of that data there. So we're going to wind this up. It actually ran a little longer than I really thought it would. So hope everyone is safe, hope everyone is doing well. So, from Larry from the hills of Tennessee, thanks for watching.